let's talk about the important question. Under what situation we should use Gauss's law and in what situation we should not. Okay? How to figure out the E field? If we have a point charge, we have a simple equation, KE over R square. However, if we have charges of different sizes and shapes, we do something differently. One way to do it is that we could cut the charges into tiny bit of dq, many of them, different dq, and then each of them creates a small amount of dE, and that dE is determined by the dq KEQR square. You treat every small amount of dq like a point, you find the dE, and all of them are going to contribute adding together as vectors, the dE from 1 and the 2 and the 3, adding together, integrating together, you find the total E field. However, notice that they are vectors. If we have a ring along the axis at this location, and this dq is going to create something this way, this is going to create something that way. Everywhere, all the small amount of dq, they create E field in all the different directions. These dE, they cannot be directly integrated. Only after you decompose them into the x component, you can integrate the x component, or a y component, or the perpendicular component. They can be integrated separately. We know that already, okay? Can we use Gauss's law? Because this integration sounds very tedious. If we have Gauss's law, it looks like in many situations the calculation can be simpler. The answer is the following. In order to use Gauss's law, keep in mind, Gauss's law is always true. Even if you choose any arbitrary shape of a surface, this equation is valid. However, it is not going to help you to do any calculation unless you can simplify this integral. How to simplify that? Either you choose a particular surface, part of the surface, so the surface is going to be parallel to the E field. For example, if you have an infinite long rod, which has an E field going like that, then I don't mind choosing a surface of a circle parallel to the E field. And then there's nothing penetrating those two surfaces. When the E field is parallel to the surface, E field is normal to the perpendicular to the normal direction of the surface. This dot product is 0. You have no flux penetrating the surface. That simplifies the integral, but still does not solve the problem. Or we would like to choose the surface, like this surface of the cylinder, everywhere on the surface. The surface is perpendicular to the E field, so that the E field and the normal direction of the surface are in the same direction. Then the dot product of E dot n becomes simply the value of E itself. This complicated integral becomes E dA integration. Not only that, we want this E field on the entire side wall of this cylinder to be equal everywhere. That's why we choose a cylinder centered at this rod, so that this integral can be further simplified. Whenever your E field everywhere on the surface is the same value, you can take the E out, and this integral becomes simply the E value, unknown E value, multiply integration of area, in this case, the side wall area of this cylinder. If we are capable of finding a surface or a few parts together, a closed surface, to be either perpendicular to parallel to the E field, we can do that. Similarly, we can do that for the spherical symmetric object. If we have a sphere outside or even inside, we can choose sphere shape. We can choose sphere shape so that we know everywhere it's the same in all the directions. Everywhere we have E field perpendicular to the surface. Inside, we also have E field perpendicular to the surface everywhere. Or if we have a shell or something like that, we can also choose spherical Gaussian surfaces. Every direction is the same, and the pink surface is perpendicular to the E field everywhere. Okay? But how about instead of an infinite long rod, how about a finite rod? When we have a finite rod, let's look at what the E field look like. At the very center, you have the same amount to your right, you have the same amount to your left. So at the very center, you do not bend. Your E field is perpendicular to the rod. However, one side and another side, your E field are going to be bended like that. When you are exactly here, all the positive charges are going to give you an E field pointing away from the charges. You have E field that way. Here you have E field that way. And when you are close to the edges, your E field are bended more dramatically. When you are close to the center, your E field is not bended much. When you have such a complicated E field, can you figure out a surface so that the surface is perpendicular to the E field everywhere? Can you figure out a surface so that the E field on the surface is equal everywhere? No, you cannot. Even though you still can choose a surface, this is still true, but you cannot simplify this integral. You won't be able to simplify that into a E field value multiplied the area. You can apply the Gauss's law, but it is not going to help you to solve for E field at all. It's not helpful. It's still true, but it's not going to solve your problem. Similarly, what if you have a ring? Yes, the E field around the ring is also very complicated. At the center, it goes away. All the up and down cancels out. At the center, you have E field pointing away. And here, you have E field going that way. Here, you have E field going that way, all over the place. Again, without particular symmetry, not being able to find a surface to be either parallel or perpendicular to the E field. In these two cases, you cannot use Gauss's law to do any calculation, even though this is still true. What about if you have an infinite large amount of plate? If you have an infinite large plate, again, you have your E field perpendicular to the plate, going away from that, okay? Now you can choose a surface to be perpendicular to your E field, and then the sidewards to be parallel. You can still apply Gauss's law. What if you have a very small piece of paper, very small, with a charge, and then in that case, you have your E field going away from the center, and then around the edges, you have your E field bend, like that. And at this edge, you have E field going away like that. Again, without the good symmetry, in this case, when you apply this Gauss's law, your calculation is very complicated. You won't be able to simplify this integral into E value multiply a particular area. So again, this is not helpful. If you have an arbitrary shape of a charge, this is still true, but you won't be able to use it to calculate the E field. Okay, so to summarize, we would like to see these are two methods. They are both correct. In this situation, you can also cut your infinite long rod into tiny bit of dq and integrating to get the total amount of E field, but that's very tedious. Due to the symmetry, we can figure out the E field at this location or at this location very easily. Same thing happens here and here. Whenever you are able to find a surface to be parallel or perpendicular to your E field, and your E field on the surface is equal and uniform everywhere, you can do this. And your problem becomes simplified into E field multiply A. Okay, but keep in mind, you want to show me you have this method and you are able to do it step by step instead of memorizing E multiply a particular area. In those situations, because you do not find a nice surface to be everywhere perpendicular to the E field or parallel, and the E field is not uniform, it's different at every location, this won't help. Okay, and then in those situations, we have no choice but to cut the entire object into infinite number of small point charge dq, and to figure out the contribution from each one of them, and then to do the integration in separate directions to figure out the total amount of E. Okay, and also that's true for when you have a 2-point charge. 1 has the spherical symmetry. When you have 2 or 3 or 4, you cannot find a nice surface to be perpendicular to this complicated E-field diagram in any location. And a particular interesting example is a capacitor. Also, when we talk about the infinite and the infinite, as long as you have a very long rod, we can approximately consider it to be infinite, as long as it's long. Here, when we talk about the plate, as long as it is very big, large, we can consider it to be infinite. Only when it is very small, this is not valid. And for capacitor, you may remember, we are going to have 2 large metal plates, and they are charged with positive charge on one plate and a negative charge in another plate. So in between them, the actual E field looks like this. If the charges are uniformly distributed, the E field inside is uniform. When you are getting to the edges, you may have some E field bending like that, but we typically ignore that. Okay? Just ignore what happens outside, and then just only focus about the center part. And then in that situation, if you consider this large enough or close to the center, we can again apply Gauss's law by choosing such a Gaussian surface. And notice that in this situation, the E field is only confined between the 2 plates. There's no E field in the other side. So this integral becomes for this entire closed surface, including both ends and the side, equals to 0 from the left, from the one end, and 0 from the side, plus the E field here multiply this one area. And that's equal to the charge in this part. And that's equal to Q in whatever charge inside this pink Gaussian surface over epsilon 0. And that's equal to epsilon 0. No, that's equal to sigma, the surface charge density sigma, multiply the area over epsilon 0. Okay? And that's equal to EA. As you can see, A cancels out. The E field inside this capacitor is equal to sigma over epsilon. In another word, it's equal to the amount of charge over the area, total area over the epsilon 0. Which means when you have a capacitor, if you have more charges, if the charges are distributed very densely on the plates, you are going to have a larger E field in between. Okay, and that's one example of utilizing Gauss's law.